Let's try a Maclaurin polynomial for x e to the x, not because it's a function I really care about, but because it illustrates a principle that we want to get at. X e to the x is actually close to a function I care about, which is x times e to the negative x, which is a surge curve. Here I'm just not including the negative just to make life a little bit simpler. So what's the derivative formula at order 0? It's just x e to the x. How about f prime? We'll go ahead and fill in the derivative there. I've got to use the product formula. So that would be x prime e to the x plus x times e to the x prime, which is 1 times e to the x plus x times e to the x. And then how about f double prime? Got to use derivative of this. Well, that 1 times e to the x, that part's easy. That's derivative is just e to the x. And then x times e to the x, have to use the product rule. Actually, we just did that, so we could copy. So we'd get just this answer again, 1 times e to the x plus x e to the x. How about f triple prime? That would be derivative of this is e to the x. Derivative of this is, hey, that's an e to the x as well. And then derivative of x e to the x, hey, we did that up here, so we can just copy that. 1 e to the x plus x e to the x. Oh, let's try that again. X e to the x. Okay, I don't really feel like doing more orders than that. I think we have enough to see any patterns that we might end up seeing. What's the derivative value? Where should we take the derivative value at x equals what? Since it says Maclaurin, at x equals 0. So what is the derivative there? Plug in 0, you get 0 times e to the 0, which is 0 times 1, which is 0. This one, 1 times e to the 0 plus 0 times e to the 0. That's all 0. That's 1 times 1, so we get 1. Here we get 1 e to the 0 plus e to the 0 plus 0 e to the 0, which is 1 plus 1 plus 0. So we get 2. Here we get 3 e to the 0s plus x plus 0 e to the 0, so we get 3. And then, what's our polynomial terms? This would just be a 0. This would be 1 times x. This would be 2 times x squared over 2 factorial. This would be 3 times x cubed over 3 factorial. So it wasn't the worst product rule in the world, but it wasn't pleasant, right? So here's a question. Could we have gotten this any other way? In a previous video, we said, hey, we know the Maclaurin series for cosine x. Let's just plug in 3x instead of x, and we got the Maclaurin series for cosine 3x. Can we do anything similar here? Well, we're not really using anything besides x here. It's not like we're doing e to the 3x. But we could say, well, we know the Maclaurin series polynomial for e to the x. Let's just write that. So we got e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus etc. That was the pattern. So what we might guess for x times e to the x would be x times that whole thing. So just copy 1 plus x squared over 2 factorial plus x cubed over 3 factorial. I'm being kind of vague here deliberately, like, are we really going on forever or just stopping at 3? It doesn't really matter in this part of the section. So now I'll just distribute the x. I get x plus x squared plus x times x squared gives me x cubed over 2 factorial. X times x cubed gives me x to the 4th over 3 factorial. And now let's compare it to this. I had a 0 here for a constant, and here I have no constant, so that works. Here I have 1 times x, and here I have x. Here I have 2x squared over 2 factorial. Well, 2 factorial is just 2, and that cancels the 2 here, and I just get an x squared, so that works. And then here I had 3 times x cubed over 3 factorial. Let's write that one down. 3 times x cubed over 3 factorial is 3 times x cubed over 3 times 2 times 1. And I can cancel the 3's there, so I get x cubed over 2 times 1. And I can rewrite x cubed over 2 times 1 as x cubed over 2 factorial, which matches that. And up here we didn't go far enough to know what the next term would be, but you could probably guess it would be what? 4 times x to the 4th over 4 factorial. And there the 4 out front would cancel the 4 and the 4 factorial, and you just get a 3 factorial, so it would all work. So one way to generate a Maclaurin or Taylor polynomial for a function that's slightly complicated is to base it on what you already know instead of having to do all the derivatives again. If you need cosine 3x but you know cosine x, just plug in 3x everywhere. Be careful with your parentheses. If it's more of a multiplication thing, you can say, well, I know the Maclaurin or Taylor polynomial for that, and then just go ahead and multiply out, and that seems to work too.